In this video, we speak about stability and see how it might be generalized to objects other than fixed points. We've talked about fixed points already, and we've emphasized that trajectories don't actually stay fixed at fixed points. All models are inaccurate, literally all of them, even in the hard sciences. Complicating factors are neglected. For example, the Lotka-Volterra model assumes that in the absence of predation, the prey species will grow without bound, but that isn't true. The prey species also has limited resources. In the hard sciences, you can be more accurate than in some other fields, but still simplifications have to be made. For example, you neglect relativistic effects if things are not moving at relativistic speeds. If an object's motion causes it to contract by 1/10,000,000th of an inch, who cares? And this brings us to the concept of stability. Because the model is only a rough estimation of reality, the idea that you can sit at a fixed point forever is also only a rough estimation of reality. The math might say you stay at a fixed point, but actually you don't. For example, if we look at the Lotka-Volterra model, the prey and predator populations are constantly being hit by random fluctuations. Harsh winters or easy winters, disease outbreaks, unusually large or small litters. Whatever the math says, the population will not stay at a fixed point. So, if a fixed point is unstable, it doesn't have any real-world meaning. It can never be seen in nature. Random fluctuations push us off it, and then the instability pulls the trajectory away. If a fixed point is asymptotically stable, then we can remain near the fixed point. We won't remain actually on it in the real world, but when chaotic forces push us around, the force of the asymptotic stability will keep us close. What about stability? what we also call neutral stability to avoid confusion. Well, a neutrally stable fixed point is a center, and the pictures we have seen look like this, with trajectories orbiting it. We saw this in the Lotka-Volterra model, for example. So we have a trajectory orbiting a fixed point. Observe that everything I said about a fixed point applies to this orbit too. Just like we can't stay on a fixed point, we can't stay on this orbiting trajectory. Random fluctuations will kick us off it. To see a fixed point in nature, it has to be asymptotically stable. If we want to see these closed curves in nature, the same thing must occur. There has to be some kind of stability property that brings us back to this orbit after we're kicked off it by random perturbations. In this video, we introduced the idea that things other than fixed points might be classified in terms of their stability. In the next video, we'll introduce a few definitions and nail this idea down.